So as Danny said, today we are going to talk about sensor localization by few distance measurements via the intersection of implicit manifolds. It's quite multiple. Hopefully, by the end of this talk, you will understand what the work is. Okay, so first of all, let's talk about. Let's talk about what the problem is. The problem of localization, and the problem in general is giving some sort of inputs to determine where the robot should be in space. It could be locally, but for example, in the left picture, we have a room with QR codes, and using the camera and which QR code we see, we can determine where the robot should be. Another kind of useful, popular example is the GPS. Try to use satellite data to determine where we are on Earth. And another way is from inside out. So we have a robot that travels the floor, and say we know how the floor looks like, and it sends a laser scan of like 360 degrees, and given the point cloud of distance measurements it gets, we can do some sort of matching to know where the robot is in the room. And let's elaborate a bit more about the last example, because we have a range of 360 degrees, of 180, 180 degrees of distance measurements. And using that, we can actually quite accurately determine the position. But one might ask whether do we actually need that kind of range of sensor of measurements, right? Maybe we can use only a few. Or how many do we need to determine the position? And why this kind of problem might be interesting is first of all, understanding the problem, right? We can do this kind of matching, but it doesn't say anything about the geometry, right? Of even one measurement, where might we be? But also, instead of like a LiDAR that does a 360 degree measurement, we can just put a simple cheap distance sensor or instead of a camera. And this also leads, besides cost, the amount of data we need to send over the network, right? Because sending an image 30 frames per second, or sending a LiDAR scan, which is 360 degrees of, say, thousands or tens of thousands distance measurements every second, it's quite a lot of bandwidth. So maybe we can just send like a couple of floats, and we already know where we are. But one simple example can show us that it's kind of hopeless, because even a range like infinite amount of points might not be enough to determine where we are. Right? We have this kind of symmetric pool with identical subgroups, and few positions where if we place the robot and take 360 degrees of measurements, we get the exact picture. So we cannot determine in which of the rooms we are. And it's not even like a pathological example. This might be a floor plan, right? If you put the robot in some apartment building, and all of the apartments look exactly the same, using only that kind of data without any more markers or landmarks we can depend on, we cannot know where we are. So, but we're not going to give up. So let's have this kind of setting where we still have a robot in the room, and I hope it's fine in Zoom. Right. So it takes a measurement, and measurement T1, for example, it does some sort of movement like translation or rotation, takes another measurement, and then so forth. And after a few, in this video we have 6, we want to know where the robot is, or not where the robot is because we cannot determine exactly, but because of symmetries maybe, but how can we reduce to a collection of points for which the robot, I hope we see that fine, and 2 guesses in the video, we want to determine where the robot might be after those kind of motion. So if you formulate that a bit, say we will call the distance measurement function h. Also, just to clarify, in this talk we're going to talk about planar rooms, a robot that can move parallel to the axis, and it can rotate about the text. So we have pretty bit of freedom, right? It can move forward and right and rotate. And the distance measurement is we get a point in the room and a direction where the robot is facing, and we get a non-negative distance measurement. So the problem is, given some sort of room, and we do some k motions in that room, like we are seeing in the video, we call them GI, G1 to GK, and say we have numbers D1 to DK, which are non-negative values of distance. We want to find all of the positions of the robot in the room, right, x, y, and orientation theta, such that if we do the motion GI on the position and then measure the distance, we get the number AI. So this is kind of the framework we are working in, and we're trying to understand a bit better this problem.
I'm told that the acoustics is not so good. Can we try and use your microphone and I shut down the music to improve the situation?
Is that better? I hear an echo, so that's not good.
Microphone should work. Yeah, microphones are disconnect.
Now it should be okay. But we're not going to hear the audience. Now we are. Okay, sorry about that. Okay, so this is the problem we're going to talk about. And okay, and the key is going to be visualizing the preimages, right? A preimage is exactly what we're looking for, is the set of, given some number D, it will be the set of all possible positions in the room, such that if we do that kind of translation and rotation and then measure the distance, we will get D. So this is like the formal definition of that. And we'll also, just for the simplicity and for being able to actually also visualize, but to analyze the geometry here, we're going to identify the rotations, right? Because the rotations are points on the circle with the angle of rotation. So everything can be embedded in the three-dimensional space. And we're going to try to understand how these preimages are going to look like. And then using the kind of school of thought of visualizing those preimages, we can actually get an algorithm to do that kind of localization. Okay, just a quick remark. The distance function is, although it's kind of piecewise smooth, is discontinuous, right? Because we have an example for even a simple polygon, right? Where we have kind of a cusp, and the robot rotates in place, and he sees the first wall, and he gets some kind of continuous change in distance. But then there's sort of a breaking point where for every epsilon that will move next from that breaking point, we will see the back wall, meaning that we get a discontinuity in the function. So this kind of makes the analysis a little bit hard, maybe, or it's kind of a very important thing to notice about that function. Okay, so we'll start from a very simple case. First, imagine that the room is an infinite half space, right? We have a line wall, and we can be everywhere. And we know that we got some integer D. And we want to ask, where might that robot be? So we have the line equation, and we can write the algebra, right? We want, given a point P, and a vector like a point on the circle representing theta, and we move the D units forward, right? We want to be on that line. This means that we got a measurement of D. And we can solve the algebra, it's not that hard, and we get the equation that Y is free, and it is the function of X and theta, right? And for this case, we get a ruled surface of, right, for every value of X and theta, we get some sort of altitude Y, as we can see in this picture. And what we get from here is that, at least for this case, the preimage is a two-manifold. right? It's a two-dimensional manifold, in this case, a ruled surface, and or like a graph even, or at least some kind of graph. And what we'll notice is because of the discontinuity in the distance function, the pre-image will not be a two-manifold, right? We cannot guarantee that, and we will see that it's definitely not a two-manifold, but it can be shown as a union of two manifolds. And let's kind of see a bit more complicated example. Say now the room is a square, say with an edge length of 2, and we get a half meter of distance measurement. And there are many places I've drawn here too, but there are many places the robot might be, and we want to know exactly where it might be. So first, we notice that getting distance measurement of half from the upper wall is kind of follows the exact same analysis we have seen in the previous example, right? Because it's an infinite line. And indeed, the bottom picture, it shows us kind of, right, the sign graph that we have seen in the previous slide. But if we project, ignore the y value, and just look at x and theta, now we cannot be everywhere, right? Because there are some points, for example, like P2 in the drawing, where if we will rotate even a little bit epsilon to the right, we'll see the right wall. So there's kind of a cutoff of that patch we have seen of the kind of ruled surface we have seen in the previous example. So, but every wall will have a similar image or similar pre-image corresponding to each wall. And if we combine all the four together, we get this non-manifold object, but this is the pre-image for half a meter for a square room. I hope that's clear enough. A more interesting example that I have, at least when I saw it for the first time, I was kind of surprised. We have this five-gon, right? It's not too complicated, it's not non-convex, but it's a simple polygon. And say we get a distance measurement of 1/3 and 2/3, right? So we place the robot, have a distance measurement of 1/3, then we rotate about, this is the r pi here, the rotation with pi radians. So we measure the distance from the back, we get 2/3, right? And here is one point, which follows that kind of logic. And you ask, even if you ignore the rotation of the robot, only what locations are possible in the room for getting that kind of measurement. And the image is that, which is kind of surprising at first. When you understand what's going on, maybe it's a little bit less surprising, but it's kind of non-trivial, at least first, to look at. And what we get is we have two manifolds which we intersect, and as long as we don't have degeneracies and the intersection is transversal, right, the two manifolds are penetrating each other, the intersection becomes a set of curves. So this is I think a nice point to mention a previous work by my colleague Barak and Danny and Steve, which actually does the exact computation both for a single pre-image and for two antipodal measurements. So what their work does is they have an algorithm, which we will discuss in a few words later, that for how to compute the projection of the pre-image onto the workspace. So we ignore the theta, but we do want to know how it looks like and compute how it looks like in the workspace. And also they actually do the algebra to get in that case that it must be either lines or parts of ellipses and nothing else. And they actually show how to compute those exactly. But that approach is very hard. The algebra, even for two antipodal measurements, is kind of hard. And it's even harder for translations and for general rotations. And it's unclear how to use those methods for more than two distance measurements. So this also gives rise for maybe a numerical approach of how to go about that. So once again, let's recall the problem. We have k rigid body transformations, right? Translations and rotations in space, and a set of k not real values. And we want to find the pre-image, right? All the poses for which we can get that measurement. Okay, so the approach is super straightforward, right? For each distance measurement, we are going to compute, or we're going to visualize or to draw the or approximate the pre-image. Then we can just intersect them, right? Because the intersection corresponds exactly to the act we are doing, right? We have a pre-image for getting one distance measurement and for a second. So if we know we got both, we must be in the intersection. And if we said that intersecting two manifolds yields us curves, the moment we add a third pre-image, we already reduced a set of points. So k greater or equal than 3 suffice to actually reduce to a point set, and from there on we just add information. So even though we at worst case need infinite number of points, at least 3 are required to actually get a pose estimate for the robot. Okay, so let's kind of go in detail of how that algorithm works. The first step of the approximation of images is kind of a simplification of a famous, I think, algorithm called Martian cubes, which goes something like that. We split the configuration space, right, the 3D space, into an n cubed grid, right? Each dimension we split to n lines and voxels, and for each voxel and for each vertex of the voxel, we compute the distance function, right? So we say if we place the robot in that point, then rotate and translate, and then measure the distance, what would we get? And we do that for each voxel. And if for a given voxel, there are two vertices, one with measurement greater or equal than the I, and one lesser or equal than the Y, then we report that voxel, because we say, okay, that voxel might have a point of the pre-image. So if the function h was continuous, that was a no-brainer, right? Because we have the intermediate value theorem. So if we have one value that is greater than the distance and one that is less, then of course somewhere inside of the voxel there should be the true pre-image point. But the function is not continuous, so this might return garbage. We will see how we tackle that later. And that's kind of it. Okay, the second step is even more trivial, right? We have now voxel clouds, each probably or hopefully approximating a pre-image, and we just overlay them and we can intersect them, right? In this case, we have two pre-images, one blue, one red. We overlay them on top of each other to get the purple intersection. And finally, once we do that enough, or at least three times, we get in an image that looks kind of like that. So we have blobs, kind of voxel clouds, each representing or each contains a possible point in space. But still, it might be a large set, and we can apply some heuristics on how to reduce that set and how to return what we think is the localization of the robot. One way to check ourselves is the sanity check, right? So first get the center of mass of each connected component, but then place the robot in the room. Okay, so we guess that it is in that point. At least in theory, we can just measure the exact same motion in that room and check whether we actually get the values we should get. This kind of very quickly filters out the noise that might be generated by the first step. Also, if we get a huge volume, right? If we get maybe a blob that is not doesn't look like a point, maybe it's like tens of thousands of voxels. Okay, maybe that is noise, so we can just ignore that, because even if it contains a pre-image point, or then right, the center of mass is so far from any relevant point that it doesn't give us it doesn't give us anything. And another kind of heuristic that we didn't implement, but one might try, is even like comparing with other sets. So, right, we take 6 distance measurements and take every combination of 4 and take the majority vote, for example, for the most likely localization. Okay, so so far sounds so simple, and it is simple to implement. But I think the nice thing is that we are able to say something meaningful about the results of the algorithm. So first of all, for each preimage, our approximation has the preimage inside of it, right? So the preimage is contained in the approximation, which by itself is kind of maybe not that interesting, right? Because if we take the entire configuration space, then we will still, the first bullet will be true. So we actually have that the Hausdorff distance of the preimage and the boundary of the approximation is 1 over n times some factor. So the higher the grid resolution, right? Let's recall that n is the number of subdivisions we do in each dimension. So if we subdivide enough, we take a fine grained enough grid, then the distance of our approximation with the actual preimage is lowered, and we converge kind of to the true result. And same holds for the intersection of preimages, right? So if the first bullet is true for each preimage, then the intersection of preimages is also contained in the intersection of approximations of preimages. And the distance is O of 1 over n. It's not that hard to see. Also, we are kind of robust to distance in errors in distance measurements, in the sense of if we know that the error is bounded by some small epsilon, then we can show that the preimage of the distorted measurement is epsilon close in the Hausdorff sense. So just to clarify, when I say the Hausdorff distance, I mean the largest distance between any pair of closest points, right? So for the first manifold, I take all of the points, and for each point, I find the closest point in the second manifold. I measure the distance and I take the maximum. I do it vice versa, and then I take the maximum between the both of the values, right? So this kind of measures intuitively what we identify as the distance between two geometric objects or between two manifolds. So that's that. And just to say that again, so if we have a bounded error, then we still get a very close approximation. Now we are lower bounded by that epsilon, which is kind of expected, right? We can do better than the error we have. And also, if you recall from the third step, right, we take the center of mass of each connected component, and this kind of raises the error, but not too much. So now, instead of knowing that the point is inside some voxel, we know it's inside a connected component. So the error is actually bounded by the diameter of that connected component, right? It's kind of trivial because by the definition of the diameter. And what we can say about the diameter is that it's bounded by above from a very trivial diameter. Like if we take, so we have row voxels in that connected component. If we organize them in a row, right, the diameter is huge. But if they are more like sphere-like, we have the lower bound. And what we will see in the actual experiments is that the lower bound is actually an upper bound for all of the experiments. So we still get very close results. And either way, both bounds are O of 1 over n. So the more precise we are with the algorithm, the larger the n is, we still converge to the true localization. But, and there's a huge asterisk, all of this discussion is up to some set of voxels, which we call blind spots, which is true for every preimage, and which is kind of lying and ruins everything I said here, but we do tackle it. So first of all, we need to understand what those blind spots are, and that is exactly what we said about the discontinuity points, or the voxels containing discontinuity points among among the distance function. So there we cannot guarantee almost anything. Let's recall Barak's and Danny's and Steve's work. What they do for the exact computation of the image is they do this kind of rotational decomposition, right? So they they say fix some theta of the robot, and then cast rays from each vertex of the room to get the composition of the room into trapezoids. And then they show that if you rotate that theta, how the trapezoid, how the structure of trapezoids changes with that theta. So those kind of trapezoids define us exactly the discontinuity points in the distance function. And if we were to compute the exact shape of those trapezoids, we know to identify which voxels are the blind spots and tackle them individually. And then we actually get the theoretical guarantees and we get completeness and all of the bullets from the last slide fall. But we're not going to do that. We show a much simpler heuristic, which still gives us 100% accuracy and works, but is not guaranteed to be complete. And this is convolution, right? For every voxel in a single preimage, we also append all of its neighbors. So, so if we maybe missed, because of the discontinuity, we missed a voxel, then we add it to the collection. So this might generate noise, but also it allows us to skip implementing the first suggestion, and it works. And also, it's very important to clarify that this discussion is only for a single preimage. Once we approximate a single preimage, the rest of the algorithm works smoothly. Also, feel free to ask questions during the presentation.
Yeah, I have a question.
Yeah.
So each manifold of each measurement has like a thickness of 3 at least.
Yeah. That's
So the cluster you get in the end is always at least 3 by 3.
Yeah. We actually tackle that in the paper. We talk about the average row, right? The row is the number of voxels, and yes, you are right. It still yields a kind of small bound, especially because the lower bound on the diameter is rho to the third, right? So it's even if rho is kind of large because of the exponential nature of what you're describing, then still we get a kind of tight or nice enough bound, so it won't be a problem. That's a great question. All right, so let's talk about results. To the left, we actually see images from the software implemented. The right upper image is a kind of a polygon of our laboratory, and we placed theoretically the robot in the green point. I don't know if we can see that in the classroom, but there is a green point in the bottom left corner. So we placed the robot there, measured four distance measurements with increments of 90 degrees each, and we apply the algorithm. And we ask, where do you think the robot is? We got 3 results, which actually, if we look at those, they are kind of symmetrical, right? There are symmetries in the room in the sense that the 3, like the forward and the right directions are short, and the back is long for all 3 points. So it's kind of hard to determine which one is the correct one, but since we strive for completeness, right, we're trying to be conservative. We do get that at least one of them is very close to the ground truth, to the correct point. The last 2 big images are images of the floor plan of actually the floor we are doing the seminar right now. And if we apply the algorithm for 2 measurements for the entire floor, we get kind of noise. Right, the resolution is bad, and we kind of get this mess of an image. But say we know approximately where we are, and we take a smaller query region with the same kind of precision, and we can draw very fine lines, as we can see in the upper image, and actually see the image. Okay, and to the right, we have a graph of the error of the closest predicted point to the ground truth. That means that we get, again, a set of number of points. We ask which one is the closest to the ground truth, to the point where we place the. Okay, so the experiment was we have a few different scenarios. We have the polygon of the laboratory, we have a polygon of the floor, and we also generate random polygons with varying spikeness and diameters. And we sample a random point inside the room, do 6 measurements, and we ask where the robot is. And we measure the error of the closest point, right? So again, we kind of check the completeness here in the sense that we do not miss the ground truth, the true location of the robot. And not only we get 100% of accuracy, as we will see in the next slide, we also get an error that behaves like 1 over n. The red graph on the top is the upper bound we have seen in a few slides ago, right? So it's that kind of factor of rho to the third times 1 over n, and it is indeed an upper bound. And the final resolution we take, the greater the less the error is. To the left, we have a table of a discussion on the success rate. The left column is the success rate of our heuristic. So we kind of do this sanity check, and we, as a heuristic, again, we take the localization point that yields the least squared error of the difference between distances for each measurement. So we have kind of a target function. Maybe it's not a very smart target function. And we take the one having the least error score, right? And for different scenarios, we get, I don't know how you looked, I think it's high, at least 90% of success rate besides the floor plan. But the floor plan is highly symmetrical, right? We have many identical rooms. So it's still, it's kind of nice to get something that is more than just 50-50 or something like that. And the next column to that is what we discussed, right? We ask, okay, we have a number of estimates. To the right, we see actually the number of estimates returned. So we have, for the laboratory, we have 10 possible positions, and we ask which, for the closest one, whether we are up to the upper bound, right? Sorry. So we ask, well, if the closest point to the ground truth is more than the upper bound, then we call it a failure. And no, we actually get 100% success rate consistently for many experiments and for many examples. To the right, we also see that the running time, actually we have even more optimized code, which pre-computes the preimage only once. So all the numbers you see here are effectively divided by 6. But we show that this algorithm, because it's kind of simple, it runs very well, or at least well, for an old hardware, a very old hardware. And if we add a GPU, it can run even faster, and it scales very nicely to GPUs, because we have this kind of for loop that can be highly parallelizable, right? There are not many dependent computations, so the more cores we have, the faster the algorithm is. And we also tried applying the algorithm in real life, right? We try to be useful. And at least in this example, we have made a makeshift polygonal room inside our lab, and we placed the robot. As you can see, the blue arrow on the floor corresponds to the blue arrow to the image. So you kind of know how to orient yourself. And for both images, we see that we place the robot in some direction. We ask the algorithm to predict where the robot is. And it indeed gives us a very, very nice prediction, both of position and orientation. In that specific scenario of various polygonal rooms, we get an error of about 2.5 centimeters and 0.1 radians, which is kind of nice. We did try it on a more general locations, and we got about 30 centimeters of error, which is a little bit worse or more worse. We're actually working on improving that. The problem specifically for those experiments were the highly inaccurate map, right? Because if you have incorrect topology of the map, right? If we have a chair inside of the lab, which the map doesn't know about, and we suddenly get a measurement which is magnitudes of order smaller, right? So the localization is entirely off. So we're working on how to improve that. Right, so let's see what we have. We have a kind of simple to implement and scalable algorithm. Oh, sorry, yes.
You chose the number of measurements is 6 that
Yeah.
you use here. Why did you choose
Well, the more you take, the less the number of
options?
yeah. Well, we show in the paper that we work for 3, 4, 5, and 6 measurements. 3 gives us a very huge set of options to choose from. 4 and 5 already reduce it quite a bit. 6 gives us, usually after we clean out all the noise, we get about 2, 3, 4, more, at most 5 possible. That's a very good question. Yeah, so 6 is kind of consistently gives us something that we can choose from.
Thank you.
Right. Okay, so we have a simple kind of algorithm. How simple? Currently, it's a single header in C++ with about 500 lines of code. We implemented it in, we added Python bindings, we integrated it with ROS. It was kind of effortless, so at least that. But besides being kind of a simple at first, at a glance algorithm, we have proofs that it works, which are kind of not hard, but kind of non-trivial, and are very specialized for the distance function, right? Because Martian cubes is not guaranteed to work in the general case, even for smooth manifolds. Also, once again, we only require one distance sensor. If we look at the robot, the images are incredibly tiny, but at the front and also at the back, but we used only the front one, we have a very cheap, simple distance sensor, like some people have in the car for doing reverse. So it works with relatively cheap hardware and yields a very low transmission bandwidth, right? We require only like 6 floats, maybe kind of payload header, but a very small message to transmit over the network, especially in ROS. The messages are, for those who are familiar, the messages are quite small. And we are robust to distance measurements, errors in distance measurements, right? Not robust to errors in the map, which leads us to the dirty laundry, right? There's a huge elephant in the room, and it is that we need a map of the room to apply this algorithm, which is non-trivial task in itself, as we have seen, right? Getting an accurate map of our laboratory is very hard, especially when there are chairs and people are moving. So we actually don't need a polygon at all for this algorithm to work. What we need to have is a way to sample the distance, right? If we had some oracle that would give us an SDF, right, a signed distance function to the room, the algorithm would still work, but we still need to get that. Also, the heuristic, the convolution heuristic we described, introduces noise. We can see in the lower picture, right? When we add this convolution, we get very fat curves. And as Bart stated, even the points are kind of have a lot of voxels in them. And also, when we are close to the boundary, it introduces noise. It's kind of hard to deal with, or not hard to deal with, but it's something you have to deal with. We do not tackle errors in odometry in this paper, which is a little bit harder than errors in distance, because even a small error in odometry, right? If we say we are at some theta degrees, but we are theta plus 1 degrees, the distances we might get for all the measurements might be extremely off. So it kind of does not correspond to a small distance in error, which means the bounds are worse. And also the runtime, we said algorithm is simple to implement, but it's n cubed, right? We do for each n for each of the dimensions, which is kind of mitigated by the scalability of the algorithm, because if we have, say, n cores, like 1,000 cores, then we kind of run in n squared, but still, it's intractable for higher dimensions and for large enough values of n, which also leads us to what is left to do, and the answer is quite a lot. And it is to improve the accuracy, right, in practice, because we want our algorithm to be useful, and we have preliminary results, which we hopefully will publish. Also, we deal only with bounded distance errors, but one might believe that the error is not bounded by some value, but is stochastic, right? It might be an infinite error, but with zero probability, and we do not tackle that. Also, we assume that we know what are the predetermined motions are. Maybe we want to optimize, right? We have done 2 measurements, and now we want to find how much do we need to rotate or translate in order to minimize the number of points we will get for the 3rd and 4th and 5th distance measurements. And also this algorithm works nice for 3 dimensions. Even for 4 dimensions, it becomes intractable, and maybe it can be applied for high dimensions, but more work needs to be done. And that's all I have to say today.